Welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm joined by Barry Blixt. Barry is the Director of Memory Marketing and Applications at Microchip, and he's going to explain why Microchip is memory. Welcome to the podcast, Barry.
Mike, thanks. I really appreciate it. It's good to be here.
It's great to have you on. Can you start off by telling us a little bit about your role at Microchip?
Sure. So from a big picture, I belong to what we call the Memory Products Group or Division, MPD. So we handle all of Microchip's standalone memory products, which are mostly serial EEPROMs and Flash. That's what my big group does. So we do everything from design, develop, manufacture those memory products. My groups are marketing and applications. So in the marketing world, we're doing things like, what products do our customers want in a couple of years? It takes a couple of years to develop these products. So we're always looking ahead. Where is the market going? From an applications perspective, where it's a lot more about today. What applications are customers trying to do? Are they having any trouble? But that also rolls into, what are we seeing that might be helpful in the future for customers? So that's kind of my world.
Sounds really interesting. I mean, obviously there's a lot of memory technologies. You mentioned you focus on EEPROM and Flash. Can you talk a little bit about how those products are used and how they maybe differ from some of the other memory technologies that people might be more familiar with?
Yeah, it's kind of funny. So Microchip, we started out as an embedded company. So a lot of our applications are microcontroller based. When you think about memory, a lot of people think about the memory in your cell phones, memory in your computer, tons of different kinds of memory. So those kind of things tend to be NAND flash, DRAM, and we don't make those things. We don't make big, giant consumer type memories. We focus on more embedded memory. That gets back to the non-volatile memories of serial EEPROM and serial Flash, serial NOR Flash. That's where we live. And we live there because that's where our main product and our customers live, in the embedded world. So where our stuff goes a lot of times is sitting next to a microcontroller or maybe even a small microprocessor for a little extra memory.
And can you just explain the difference? You mentioned that, the two technologies are both non-volatile, but how does the EEPROM differ from Flash?
That's a good question. So it seems like it might be a hard answer. From a user perspective, it's actually pretty simple. I'll kind of go into some numbers a little bit, try not to bore everybody, but serial EEPROMs tend to be at the low end of the capacity. So they generally go from 1 kbit, so that's 1,000 bits, up to 1 megabit. And that's where Flash takes over. So Flash takes over from 1 megabit all the way up to 2 gigabits. And they're very similar technologies. Flash was kind of developed out of EEPROMs. The thing they have in common is they're both non-volatile. So you store something in there, ones and zeros, and it's still there. So in that sense, memory we kind of joke around, well, it's kind of a boring product. It doesn't really do very much. We have lots of fancy BUs in our company, FPGAs, that have all these nice demos, blinking lights, lots of cool stuff happening. And then you look at the memory, and what our part is supposed to do is, well, it's still ones and zeros. And we look at it again in a couple of years. Now the ones and zeros haven't changed. And that's kind of our world. And it sounds easy, but it's really not that easy to make either the lower end serial EEPROMs or the higher end Flash to be able to do that. I could talk a little bit more about the differences. That it's more than just capacity. So the low end serial EEPROMs, they have a different methodology of how they program, how they move electrons around. They tend to have much longer data retention, 200 years. So you can look at an E squared in 200 years, maybe, and see and it still has that data. The other thing it does really well is you can change that data very often, 1 million times per the data sheet, even more in some cases. Flash the way it moves electrons is a little more violent. It tends to have less data retention, more like 20 to 100 years, and significantly fewer erase write cycles are possible, more like 10,000 or maybe 100,000 rather than a million. So those are the big differences.
And do people use them for different things, presumably?
Yeah, actually, they kind of do. So if you think of an E squared with a small amount of memory again, where we see a lot of use there is in calibration data. So we're building something, maybe it's a robot or a power meter or something. And when the device is manufactured, it has some sort of small amount of data that says, okay, these are the parameters that it was manufactured under. I write them in here. I refer to those maybe later, and that's it. A lot of cases, probably most cases in E squared, even though it's good for a million erase write cycles, it gets one, but that's all it needs to do. Flash, on the other hand, tends to be more program memory. So it's pre-programmed. Maybe it changes as a customer says, well, we've improved how we want this robot to work. So we're updating, we're going to flash the memory. You hear that term a lot. So those are kind of the big differences. E squared, more calibration data, smaller amounts of data. Flash is more program memory, bigger amounts of data.
That makes a lot of sense to me. I've got to ask this question. It's a bit cheeky, Barry, but E squared and Flash, they've been around for quite a long time. I keep hearing about, new memory technologies. Why is it these two technologies are still around and still successful?
So that's a really good question. If you go back maybe 20 years, 25 years, when all this really started, you'll see ROM memory moved to EEPROMs. We learned how to erase memory and then rewrite it. Now it's all electrically done in situ a lot of times. And other memory technologies have come out in the last 15 years or so, SRAM, MRAM. And those memories tend to be, if I could say, pretty cool memories. They take advantages of non-volatile memory and volatile memory and put them together. So they tend to be really fast. I said E squareds have a million erase write cycles. Some of these are unlimited or virtually unlimited, billions of erase write cycles. The problem is they're more expensive to make, maybe 10 to 100 times more in cost. Flash and E squared have just found that spot where it's very efficient, very effective memory at a really nice price point. And none of these other memories have really been able to displace that.
And that makes sense, but maybe we're heading back towards this memory is a bit boring. So, I mean, is it really boring? What's happening? What's changing? What are the trends in the market?
So I joined this company 20 some years ago and I thought, I can't possibly stay in memory. But here I am after all these years because I do find it interesting. And I find two things interesting. One is that the things that our customers use memory for, all sorts of applications. The other one is, I said before how memory really doesn't do very much, but it's really hard to get it to not do very much. By not doing very much, you don't lose a bit here and there. How do we do that? Well, that's where a lot of the innovation comes from. It's internal, lots of design. What our customers are looking for, probably more than anything, is improved PPM fail rates. So years ago, I'm going to say a typical, not an E squared, but maybe a microcontroller is maybe 100 PPM. So out of a million parts that ship, 100 fail. Today's E squareds are less than 1 PPM. And we're starting to look at PPB ranges. And it just doesn't just happen. It's from the design. A lot of it's from the extra testing that we've developed over the years too. So that if we can see that, well, here's a bit within a part and it's okay now, but we have a feeling, or the data shows it might fail early, we won't ship that whole part just based on one bad bit. So that's internally, that's what gets me excited. I like that. I suppose customers do because nobody wants parts to fail. The other thing we're seeing is kind of the things you'd expect, trends from people need more memory. We're seeing a trend to simpler buses. SPI is a popular bus, has 3 or 4 connectors to a microcontroller. I2C has 2. Now we're seeing people who like 1 wire connected to the microcontroller. So those are the kind of things that we're working on.
That's interesting. I'd like to just jump back to that failure, because you mentioned you can see failures or potential failures when you're actually manufacturing. So presumably it's not a case of something, wearing out like a mechanical part. What does failure look like to a memory?
That's a pretty interesting topic. If you can picture a memory cell, so there are 2 gates and there are electrons flying back and forth, whether it's a 1 or a 0, there are a couple things that can go wrong. The basic things that can go wrong is that the electrons get stuck, maybe on one gate or another, or maybe in the oxide layer between the gates. And that's going to happen naturally. As you go back and forth, electrons are going to be left behind. The fail happens when more than half the electrons get stuck. And then the sense amp, which measures where are the electrons, can't tell anymore. It looks like they're half here and half here. Is it a 1 or a 0? We don't know. That's almost like a mechanical failure. All semiconductors are going to fail at some point. The real trick is, how do you get those failures way out in time and not immediately? Early fails tend to be things like a manufacturing defect. Everybody sort of clean rooms. If there's a tiny piece of dust that's flying around and ends up on your product, on your die somewhere, that's going to lead to a fail someday. There are even very rarely package fails where something gets cracked in packaging. Maybe something doesn't get connected right. So we try to do two things. We try to eliminate the number of fails, but they're going to happen. That's when we add the testing to say, well, it's okay if a couple parts on the whole wafer are no good, but it's not okay if they get out to the customer. So that's where the testing comes in. And we talk about a bathtub curve. I'm making shapes with my hands that nobody can see, but if you can picture a bathtub cut in half, there are early fails on the one side of the bathtub, the cross section. If you can get through those, then you'll reach the bottom of the bathtub where there are no fails. And then the part starts to wear out at the end when it goes up the other side of the bathtub curve. So what we're trying to do is make the bathtub wider and spread out the fails so that we get fewer early and fewer later. I get kind of excited about this topic because I think it's pretty fascinating.
That's pretty cool. If you can wipe out those early fails, you got that flat bathtub bottom. I love that analogy.
That's where we like to live. Everybody wants to be nice and cozy in the bathtub.
Fantastic. I mean, talking about reliability, I guess that's one of the challenges when it comes to, some of the markets, like, for example, automotive, where we're seeing a lot more electronic content. Presumably that's putting new demands on memory.
Yeah, it's pretty interesting how much content, semiconductor content, is in automobiles. Cameras all over. I mean, we bought a new car. We tend to let our cars go for a long time. So all of a sudden, we're looking at 10 years of new cameras and new things all over our own personal car. And I'm thinking, wow, there's so much to figure out, but all those need semiconductors. In my world, all those cameras need an E-squared. We talked about calibration data. That's what the E-squared does. The camera has to know, what should I focus on? Where should I end up? What should I be looking at? That gets put in the E-squared. So I talked a lot about E-squareds and NOR flash in general, but to get down specifically with Microchip, where we think one of our advantages is in a lot of applications like automotive, where it's not good if a 30-cent part fails on your car and all of a sudden it can't start. That's pretty bad. So that's why a lot of our customers are looking for PPB fail rates that just can't tolerate any fails. So we tend to have a lot of customers in that kind of world: automotive, industrial, medical, implantables. You don't want your pacemaker to go bad, that sort of thing. Where there's some applications, honestly, where you don't really care if parts start to fail. A toy, maybe that's even a good thing. If your kid's loud and no obnoxious toy fails, you can finally throw it out. But that's not how it works with a car or something that costs real money.
Yeah, makes a lot of sense. That 30-cent part making, that car costing tens of thousands of dollars fail is obviously not good.
Yeah, we hear about that.
One of the things as well I'm interested in is memory. I mean, it's generally seen as somewhat of a commodity market. So it's a very commercially driven market. So what are the changes in the market, the way memory is produced, and the things impacting on price and availability?
So that's a good point. Memory is, from a high level, you can almost say, wow, all memory is the same. But as a marketing guy, I like to say wow, there aren't really any true commodity markets. Even if you go to the grocery store and look at milk, there are all sorts of different options. There's soy milk, there's 2%, 1%. There's the store brand, there's the higher price brand from the dairy down the street. So there's something for everybody. So everybody needs a different level of quality. So that's where we try to play a lot. Our value add is we are looking for customers who are looking for more out of their memory products. We're starting to add new features. We're starting to add some voltage protection features, which are really nice if you have a application with a very spurious voltage range and you can go up and down. That might cause the micro to do funny things. And one of those funny things might look like to the memory device that, oh, you're trying to write something here, but you're really not. So we can turn off that memory device. So we're doing things like that, pre-programming, improving quality. Those are the things that we're really focusing on today. And bigger densities. It's kind of a trite saying that the software guys always want more memory, but it's true. We're seeing our average device density move up as customers need more and more memory.
And I mean, one of the things I think I've seen on the Microchip website is you do some clever stuff around adding extra features to differentiate. So whether that be, I think accessory authentication is one. Can you talk a little bit about that and maybe some of the other differentiated applications?
Yeah. So what you're talking about is we have a couple devices. There's one interesting application. Imagine you have a vacuum cleaner and you have lots of different attachments on the end of it. And those attachments are powered. Sometimes they have a little a motor on the end of it. And it's important that the system knows which attachment is being attached, how much voltage should I be sending down. Another good example of that is doctor's tools. We just work with a customer who a dental tool that they can put a tool against your tooth. It sends in sonic waves and it can look inside your tooth, no x-rays or anything, and just say, oh, there's a crack, or here's what's wrong. Here's a cavity. But you don't want that going into every person's mouth all day long, right? So you have to take off the end and put a new one on. And what our device can do is, in a pretty simple manner, authenticate really quickly to say, oh, this is the right end piece, or here's the voltage that's in this end piece back on the vacuum cleaner. Or another one we've worked on in surgical devices is, oh, this device has already been used in somebody. They only get used once. That we don't want to use that one again, so we better throw it out. So that's a lot of those are on what we call our single wire product line. It's amazing how many applications there are like that, where people say, oh, I just want to make sure what's attached at the end here. And maybe I just want to make sure I haven't used it before. I want to make sure what it is, that sort of thing.
That's amazing. I mean, it sounds like there's this vast range of applications where memory is actually really crucial. It's not something off to the side. It's a core part of it. I mean, do you have any other examples of some of those perhaps surprising examples of systems that really rely on memory to function correctly?
So probably my favorite is hearing aids, where if you talk to the hearing aid companies, they all say the same thing. Like, wow, we could help so many people, but people don't want to admit they're getting old. I get that. When I started years and years ago, the hearing aid companies were saying we need somewhere around 64 kbits of data. They were putting some of their program memory in that, along with the other semiconductor components. Today, they're using, I've seen up to 8 megabits. And what they're doing is the software guys at the hearing aid companies are just brilliant people. And they're creating more and more interesting software algorithms to help hearing aids. That's half of what the memory does. The other half is you go to your audiologist and they load up your program and you say, I'm having trouble hearing. And they'll tell you, well, next time you have trouble, push this button and we'll record what's going on. A classic example is in a restaurant, and you're sitting with a group of people in a loud restaurant and all you can hear is the background noise. You can't hear your own table. So you'd push the button in your hearing aid. It writes a bunch of data into that E-squared, take it back to your audiologist who says, oh, I see what's going on. Let's make this tweak. And it goes back and forth. So the E-squared there is being used, or the flash in some cases, is being used for two different things. We talked about before, both of them that's kind of calibration data that it's recording, but it's also, here's the program memory. That's one of my favorite applications. I found that really interesting.
I love that. I mean, just to maybe sum up on the products, we seem to have covered an awful lot. I mean, can you just give me a quick overview of where you think Microchip's, real strengths, real differentiation is in memory?
Our real differentiation is you can rely on our parts. We recognize that, and we talked about it before, that it's pretty important that memory has a good price point. It's not the core of a lot of different applications, but it's needed everywhere. Everything needs memory. Where we think we're best is where the memory, whether it's EEPROM or NOR flash, that you can rely on. We tend to have really excellent supply. We make a lot of our own parts. We design everything we make. We have lots of customer support, and we have the right products. We have everything from a teeny tiny little EEPROM and a smallest package you can imagine, die size, all the way up to a big giant serial flash part. So it fits along with Microchip's strategy of the core of in our world anyway, the core of the application is the microcontroller. And whether it's whatever the peripherals are, memory, analog, A to Ds, whatever, we have a lot of it built onto the microcontroller, but we have some off the microcontroller too. If you need an inexpensive microcontroller with a lot of memory, we can handle that. Or sometimes it's better to just buy a microcontroller with memory on board. That's fine too.
That sounds great. I mean, you've talked a lot about, really quite different things in both the E squared and the flash market. I mean, how do engineers work out what the right product is? You mentioned support, but if an engineer is trying to go through a decision, is there a process or some things they need to think about?
It's the main thing to think about is when to start thinking about it, if that makes sense. So what we find is a lot of engineers, and it makes perfect sense. You start out with the logic. What are we trying to do here? What problem are we trying to fix? Then you start looking at, well, what's the logic behind this? Is it a microcontroller? Is it a microprocessor? Is it an FPGA? Then engineers will start looking around it. Well, okay, what type of analog stuff do I need? What are my power requirements? And somewhere around that time, you start thinking of the memory. What we find is people get in trouble when they think of memory too late. Like, oh, right, memory's pretty simple, but maybe it's not that simple and I don't have enough pins on the microcontroller, or wow, I selected EEPROM and I should have chosen a flash. That's where we see people getting into a little bit of trouble. So that's probably the thing we just like to say, well, think about the memory. It's not first, but it's maybe a little higher up the list than you think.
I love that. I mean, do you have any other engineering advice that you'd give to listeners? So it could be about memory or anything else.
So I would say specifically about memory, you have a lot of choices, and it's actually if you think about it ahead of time, it's a pretty simple decision path. It's really how much non-volatile memory do you need? And then you start to think, well, if it's a teeny tiny little amount, maybe you can find a microcontroller that has it. If you need a little bit more and it's for calibration data, it's an E squared. If you need a lot more, it's a flash. Then you start to think of, well, which communication bus do I want to use? I squared C, which is really the most common, SPI, which is second most common. You could think about the single wires that we talked a little bit about. And then it's things like, how much room do I have on the board, package options, pricing, voltage, temperature. But the main thing is it's almost how much memory do I need? And that'll guide you right to almost the exact parts you want, because there's not much overlap between EEPROM and flash. If it's 1 gig and below, you're looking at an E squared. If it's 1 gig and above, you're looking at NOR flash.
Perfect. I mean, that definitely simplifies it for me and hopefully other people listening. Barry, this has been, really fascinating. We've covered an awful lot about memory. If people are listening, have got questions, or they'd like to know more about Microchip's memory, where's the best place to go?
So the best place to go is our Microchip webpage under the memory section. We have a lot of pretty detailed videos, some of them just on general memory, some of them on memory that we don't even make. We talked about NAND flash, and we talked about DRAM. We have videos, 2-minute videos on that sort of thing, so people can at least get educated. Then we also have more technical videos about maybe how to do something as complicated as wear leveling, where I need more than 1 million erase write cycles. How am I going to do that? Well, there are ways that we can help you do that. That's the best place to go, is our webpage.
That's awesome. Barry, this has been amazing. Thank you so much for explaining why Microchip is memory.
Appreciate it. Thank you.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.